first photos from the 3200 megapixel camera. The Rewalk Restore Exosuit gets approved. And finally, an environmentally friendly, plant-based supercapacitor. Stick around to find out more in this episode of News Bytes. Hello and welcome to Advanced Ingenuity Labs, your insight into technology. I'm your host, Aisha Sharif, and this is News Bytes, where we cover innovative developments in the latest technologies. The world's largest and most powerful digital camera is nearing completion at the U.S. Department of Energy's SLAC National Accelerator Laboratory. Once complete, it will be installed at the Vera C. Rubin Observatory, which is currently under construction in Chile. When installed, it'll take panoramic images of the complete southern sky for 10 years. The collected data will be entered into the Rubin Observatory Legacy Survey of Space and Time, a project that aims to compile a massive catalog of galaxy images and create the first motion picture of the universe. Recently, an enormous milestone was achieved when the team successfully took the first ever 3200 megapixel photos. They chose a variety of objects to be pictured, which include a head of Romanesco, a type of broccoli, which was chosen for its very detailed surface structure. The Flammarion wood engraving, which is often used to invoke the scientific quest for knowledge. A collage of the camera team at SLAC and various logos from organizations involved in the project. And finally, an image of Vera C. Rubin, the scientist for which the observatory is named. This camera's impressive performance requires 189 sensors, known as charge-coupled devices, or CCDs, each measuring 16 megapixels. The CCDs are packaged into units called rafts that make up the camera's focal plane. It took over 6 months for each of the rafts to be inserted into a grid for the focal plane. The focal plane has some truly extraordinary properties. Not only does it contain 3.2 billion pixels, but its pixels are extremely small, about 10 microns wide. And the focal plane is so flat that it varies by no more than 1/10 of the width of a human hair. This allows the camera to produce sharp images in very high resolution. At more than 61 centimeters wide, the focal plane dwarfs the 3.5 centimeter imaging sensor of a full-frame consumer camera. According to the press release, the photos are so large, it would take 378 4K ultra-high-definition TV screens to display one of them in full size. The resolution is so great that you would be able to see a golf ball from 15 miles away. And the sensors can spot objects 100 million times dimmer than what is visible with the naked eye. Joanne Hewitt, SLAC's Chief Research Officer and Associate Lab Director for Fundamental Physics, says nearing completion of the camera is very exciting, and we're proud of playing such a central role in building this key component of Rubin Observatory. It's a milestone that brings us a big step closer to exploring fundamental questions about the universe in ways we haven't been able to before. The camera will study dark energy, dark matter, and create the first motion picture of the universe. The team is now integrating the focal plane into the camera body along with its lenses, a shutter, and a filter system which will allow the night sky to be observed in varying colors. The finished product will be around the size of an SUV, and final testing will be conducted in mid-2021. Let's talk about robotic exoskeletons. We've seen them in movies, utilized them in video games, and in 2014, Matt Ficarra, paralyzed from the chest down, walked down the aisle on his wedding day with the assistance of a gait training exoskeleton suit. Robotic exoskeletons are already helping medical professionals get through long hours of surgery and have been used to assist in mobility for over a decade. A team of U.S. researchers recently published the results of a multi-center, single-arm trial of the Rewalk Restore Exosuit for gait training in individuals undergoing post-stroke rehabilitation. This exosuit is the first soft robotic exosuit cleared by the FDA for use in stroke survivors with mobility deficits. The device is to be used for individuals with hemiplegia undergoing stroke rehabilitation under the care of licensed physical therapists. Hemiplegia causes weakness of the ankle, which limits the ability to clear the ground during stepping and hinders forward movement. Restore is designed to increase ankle plantar flexion and dorsiflexion, allowing a more normal gait pattern. This robotic exoskeleton was found to be safe and reliable during treadmill and overground walking under the supervision of physical therapists. Motors mounted on a waist belt transmit power through cables to attachment points on the insole and the patient's calf. The sensors clipped to the patient's shoes transmit data to a handheld smartphone controller used by a trained therapist to adjust levels of assistance and to monitor and record key metrics of gait training. The trial enrolled 44 participants with post-stroke hemiparesis who were able to walk unassisted for 1.5 meters. The protocol consisted of 5 days of 20-minute sessions of treadmill and overground training under the supervision of licensed physical therapists. To assess the therapeutic potential for restore and rehabilitation, the researchers also explored the effects of the device on maximum walking speed, measuring participants' walking speed in and out of the device, using the 10-meter walk test before and after the 5 training visits. The trial determined the safety, reliability, and feasibility of the device in this stroke population. Dr. Karen Nolan, Senior Research Scientist at the Center for Mobility and Rehabilitation Engineering Research at Kessler Foundation, explained, "We found that Restore provided targeted assistance for plantar flexion and dorsiflexion of the paretic ankle, improving the gait pattern. This is an important first step toward expanding options for rehabilitative care for the millions of individuals with mobility impairments caused by ischemic and hemorrhagic stroke." The trial's exploratory data indicated positive effects of the training on the walking speed of participants during exosuit-assisted walking and unassisted walking. More than 1/3 of participants achieved a significant increase in unassisted walking speed, indicating the need for further research. The future of robotics in medicine is dynamic. I can't wait to see where it takes us. How do you see medical robots being utilized? Let me know in the comments. If you enjoy this video and find value in our content, you can help us by sharing it with others. Also, leave a comment as we want to hear from you. And consider liking the video and subscribing to our channel. You may also click the notification bell if you don't want to miss our upcoming videos. To stay informed about our upcoming training courses and camps here at Advanced Ingenuity Labs, visit our website at advancedingenuitylabs.com and sign up for our email notifications. Scientists at Texas A&M University have demonstrated a plant-based supercapacitor with excellent energy storage potential. Supercapacitors are able to charge nearly instantly and discharge huge amounts of power when needed. Recently, supercapacitors have been making fascinating advances in being built from sustainable materials, such as plastic bottles, hemp, and even cigarette butts. Researchers at Texas A&M are working with lignin, a natural polymer that gives plants and trees their rigidity and glues wood fibers together. Lignin is produced in vast amounts as a waste product during the paper manufacturing process. They hope to utilize lignin to boost the performance of a material used in supercapacitor electrodes called manganese dioxide. The nanoparticles of manganese dioxide offer a number of benefits over other solutions, but the electrochemical performance is where it tends to decline. The study's author, Hong Liang, says manganese dioxide is cheaper, available in abundance, and is safer compared to other transition metal oxides like ruthenium or zinc oxide that are popularly used for making electrodes. But a major drawback of manganese dioxide is that it suffers from lower electrical conductivity. However, past research suggests that lignin, when used with metal oxides, enhances the electrochemical properties of electrodes. According to the researchers, there haven't been many studies that combine manganese dioxide and lignin. In order for the researchers to understand how lignin could enhance the function of manganese dioxide, they designed a supercapacitor in which these two components formed the essential elements. First, using a common disinfectant, the team purified the lignin. Heat and pressure was then applied in order to break down the liquid, allowing the manganese dioxide to be mixed with the lignin. The supercapacitor was assembled by coating the manganese dioxide and lignin mixture onto an aluminum plate to form an electrode, and was then paired with another electrode made of aluminum and activated charcoal with a gel electrolyte in the middle. According to the researchers, the new device is light, flexible, and cost-effective, which increases its potential to be used as energy storage elements in vehicles. In addition, they reported that the plant-based supercapacitor withstood rigorous testing and found that the electrochemical properties remained stable. Also, it retained its ability to store an electrical charge over thousands of cycles. Hong Liang says, integrating biomaterials into energy storage devices has been tricky because it is difficult to control their resulting electrical properties, which then gravely affects the device's life cycle and performance. Also, the process of making biomaterials generally includes chemical treatments that are hazardous. We have designed an environmentally friendly energy storage device that has superior electrical performance and can be manufactured easily, safely, and at a much lower cost. That's it for this episode of News Bytes. As always, if you enjoyed this video and want more, leave me a comment and consider liking and subscribing. See you next time.